All right, in this video, we're going to go through some applications of Newton's law of viscosity, see how it works, see how we can apply it to an example. So if you recall Newton's law of viscosity, very important equation in fluid mechanics, it says that the shear stress is equal to a constant, which we call the viscosity, times du dy, which is the slope of the velocity, u, in the y direction. We'll draw some pictures, hopefully expand on that a little bit more, but this is a really important equation. It helps us understand 1D flow, right? Can help us determine shear stresses. So again, we have two kinds of stresses, shear stress and normal stress. If we want to understand fluid flow, we need to understand both of them. This is how we can attack the shear stresses. It's useful for thin layers of fluid. That's what we'll do in this example problem here. We can determine and understand fluid friction. Right? So fluids are going to resist motion. That's what their viscosity does. And we can understand the friction in fluids, how they resist that motion using Newton's law of viscosity. We can use this sometimes in cylindrical systems. We're going to do a cylindrical system as a homework problem. If the diameter is large and a gap is small. So that's like a lubrication system where, right, there's, say, a rotor that's rotating this way in a stationary stator. The fluid flow is going to look like this. So this is what you're going to do as a homework problem, right? This is the wall, the stationary part, and this is the rotor. Effectively, this is going to look like a simple 1D flow, like the example problem that we're going to do here. Slightly different because we're going to have to understand forces and torque and some things like that. So it'll be a little bit of extra mechanics, but not extra fluids. So what we're going to do in this example is determine our terminal speed down Splash Mountain. If you don't know what Splash Mountain is, sadly, it doesn't exist anymore, and you will never get to ride it. But maybe you've ridden a log ride like this. So Splash Mountain is used to be a ride, really famous ride at Magic Kingdom at Disney. And you're in this big boat, and you go down a slide and then splash at the bottom. We're going to look at the fluids problem of this, which is the thin layer of water that is flowing under the boat that you're gliding on, and see, given that thin layer of water, how slippery is it and how fast can we go? All right, so this is our basic system. Here's our boat. Here's you getting ready for a picture. There's your friend. And we want to know how fast we can go riding on this thin layer of fluid. So there's a thin layer here of thickness that we'll call H. So I have known in quotations because these are somewhat made up, but not totally made up. So this H value, that thin layer of fluid, is very thin, less than a millimeter thin. Your mass of your system, right? So the boat plus all of you people, we'll say is 800 kilograms. The length of the boat is 4 meters, right? You have a couple rows of people, and the width is 1.6 meters. So you have enough room for two people next to each other. And you're going down Splash Mountain, and you go at an angle of about 40 degrees. Okay. So that's how you're traveling down Splash Mountain on this really thin layer of water at 40 degrees. And we're going to try to find what's our terminal velocity, terminal speed. So the basic equations that we have are the sum of all the forces equals mass times acceleration. Right? These are vectors. And we have our fluids equation tau yx, the shear stress, equals the viscosity times the slope of the velocity. Our assumption, until we prove this later, we will prove this later, is that we have a linear velocity distribution. And we have the no slip condition. So those are kind of assumptions, but assumptions for now. So this is kind of a mechanics problem, so we need a free body diagram. We have our boat. The force of gravity, right, Fg equals mass times gravity. That's pointed exactly down. This angle here, theta, we said was 40 degrees. There's a normal force in this direction. That's right, the boat sitting on the slide, keeping us from falling down. But that's not super exciting. We're going to orient our axes with the boat rather than with Earth, because that will make our geometry a little bit easier. So we'll say we're sliding down. We'll angle our axes y and x so that they're kind of in the same idea as the boat. So we have a normal force, and we have what we'll call Fx. And then in the fluid layer, we are resisting motion, right? So we're stopping us from sliding down the hill. And that is here fluid friction. And the force of that is our shear stress times the size of the bottom of the boat. Right? So a force is a stress over an area. So let's do a little bit of mechanics. So we have the sum of all the forces in the x direction equals the mass times the acceleration in the x direction. If the acceleration equals 0 at terminal speed, then we can say that the force that's trying to push us down the hill, Fx, plus tau yxa must equal 0. Okay, and the force trying to push us down the hill, we have to do a little bit of trig, I guess, but that's right. The overall force of gravity is mass times gravity. So this is mass times gravity, and then we get a sine of the angle. So this is mass times gravity sine theta plus tau yx a is equal to 0. Okay, and that's going to tell us that right, the force trying to push us down the hill is equal to the force trying to hold us up, which means we're at our terminal speed. So that's the mechanics part. Now we have to zoom in on the water itself to see what's happening. So let's zoom in on our film of water. So we're headed down the hill. This is going at a speed capital U. That's the boat. So that's going at our terminal speed. And then the slide is not moving at all. So what the water looks like is Again, we have a no-slip condition at both walls. So what that means is our water film looks like this. And again, we're assuming that it's linear. I'm telling you that it's linear. Future us will prove that it's linear. But for now, let's just go with it. And it's linear there. The other thing that we should write, this dimension here is what we've called little h, that gap, that film of water. All right, so du dy. What is du dy? Du dy is this slope, right? We have, again, the y dimension and the x dimension, which we've defined as x, the way the boat is going, and y is the direction of this little gap. So this slope here is du dy. So we have to figure out what the slope is. This is linear. So we have a linear velocity gradient. So du dy is constant. It's just a number everywhere. What we really need is to evaluate it here, right at the bottom of the boat. That's where the friction is happening. That's where we're resisting the boat's motion. That's where the boat is feeling the fluid friction. That's the location that we need to evaluate the fluid friction at. But because the slope is constant, the shear stress is actually going to be the same throughout the entire film of water. So let's do that. Du dy is slope of u, right, which is the velocity in the x direction, which is just rise over run. So in this case, it's u boat minus the velocity of the slide, which is 0, divided by the y position of the boat minus the y position of the slide, which is 0. So this equals u boat divided by the gap. So this is simple because we have this linear velocity profile. So we can go back to our previous math and say that mass times gravity times sine of theta is equal to viscosity times u boat divided by h times the area, right? So this here is our shear stress. Now we just have to solve for u boat. Using the dimensions and things that we know. So in this case, u boat is mass times gravity sine theta times h divided by, we'll call that the area of the boat, area boat times viscosity. So when we plug in all of our numbers, we should get the velocity of the boat. Last thing we need is the viscosity of water at 20 C. So this is about 1 times 10 to the minus 3 Newton second per meter squared. We can find this in the back of our textbook and look it up, or we can look it up in a different engineering toolbox. Okay, when you get to this point in a problem, now we have to deal with the units or dimensions of the problem. So let's check our dimensions, or check our units. So we have mass, which is kilograms. We have gravity, which is, right, meters, not meters squared, meters per second squared. We have sine theta, which is sine of an angle, which doesn't have units. And we have height, which is meters. Then on the bottom, we have the area of the boat, which let's say is meters squared. And we have this viscosity, which is newtons times seconds per meter squared. And we got this kind of weird soup of units. So let's make sure we're actually doing the right thing here. So down on the bottom, right, we have a newton. And we have to remember what exactly a newton is. So a newton is equal to a kilogram meter per second squared. Kilogram meter per second squared. I always remember that by doing, right, what is a newton? It's a force. So you can find something like, right, mass times gravity would give you a force, or mass times acceleration. So that's a mass times an acceleration unit. So that makes sense. So up here, we can cross out things. This guy is a newton, and that guy is a newton. So that's cool. That is a meter squared, and that is a meter squared on the bottom. So what we're left with is a meter on the top and a second on the bottom. So that gives us nice units of velocity. That's what we wanted. We wanted the velocity of the boat. In this case, if we plug in the numbers in the units that we have them, we will get it in meters per second. So what I'm going to do is throw in all of those numbers, and I'm going to double check, and I'll get a, sorry, not a mass, I'll get a velocity of Splash Mountain, which is about 23 meters per second, or about 50 miles per hour. So hopefully this video shows you a little bit how we can use Newton's law of viscosity. Right, one of the kind of key things for that is understanding this guy, the velocity gradient, or the slope of the velocity. We'll see a lot of different velocity gradients, and we'll have to get kind of good at that. We'll do some practice in class and in future videos as well. All right, that's all for today's fluid mechanics. I'll see you next time.